The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha, everyone. I'm geologist Philip Ong, here with Mr. Dane DuPont from HawaiiTracker.com. Aloha, everyone. Very, the Hawaiian Volcano Education and Resilience Institute from HawaiiTracker.com. Aloha, everyone. Very. Dane, I'm getting some feedback. Education and Resilience. Sorry. I'm hearing everything I'm saying coming back to me. All right, testing. Sorry, you guys. All right. Aloha, everyone. I'm geologist Philip Ong, here with Mr. Dane DuPont from Hawaii Tracker and HVERI, the Hawaiian Volcano Education and Resilience Institute. Today is Thursday, September 21st, 2023. And Kilauea's eruption that we were covering last week has ended. So we'll recap the end of the eruption. We have a special interview this week with USGS scientist in charge, Ken Hahn. And of course, our usual review of the monitoring instrumentation and time lapses, which we'll try to get through a little more quickly since we have the interview today. Dane, how are you doing today?
Doing pretty good. You know, trying to figure out all the tech issues, and apparently we didn't get them all sorted out. So hopefully this will go well. We'll see.
Yeah, so far so good. Yeah, we'll see about the interview later on. We're trying something new, just so you guys know. But that will be coming about halfway through our program today. So if you got nothing to add, Dane, we'll get into it.
If anybody's got any questions, you know, maybe we can get to them at the end, but we'll drop them in the chat, and we'll try and get to them if we can.
Yeah, so thanks, Dane. Yeah, lots to discuss this week. We probably can't get to all of it this week to add our interview in here today, but we'll try to cover the bases and we'll leave some stuff for next week as need be. So let's get ourselves started here. Let's switch the screen around and put up our tags. And here's this week's Hawaiian Volcano summary. Kilauea has stopped erupting after 6 days, lasting from September 10th to 16th, 2023. In that short time, it covered about 500 acres within a caldera, including a large part of the downdrop block that was created in a 2018 collapse. That covered the eastern rim of Halemaumau crater and a majority of that inner crater floor, but did not cover the southwest part of that inner pit, which has been uplifting throughout the eruption, and a little bit more recently as well. So gas emissions have really dropped off as well, ending the primary hazard to people from eruption. That's the benefit of ending the lava output. The gas output also ends. However, even at these background levels, this can be an issue for people who are sensitive living nearby the volcano and downwind areas as well. So the hazard has passed. We'll recap the happenings on a volcano during our full update and hear from the USGS scientists in charge. But what you guys see on screen here is the live camera from the USGS of those newly constructed vents, which were built over the course of this eruption. So I'll play back for you guys here, animation that compiles the evolution of those vents over those 6 days and a few days since, showing how fountains began much more widespread. You can't see the full frame of view on screen here. But over time, they focused to these group of 7 main cinder cones, which grew and moved as the lava river carried the output away into the crater. There are another 7 cones further upslope out of the field of view here. And once eruption ends, you see just spots of glow coming from the crater floor and from the pit there. So ending very abruptly and resulting in a set of thermal maps released by the USGS showing the evolution from September 11th to 12th, 14th, and 15th, where the brighter colors, the reds, are the actual fissures, the fountains of lava. Yellow is the ponded lava and lava flows. And blue is the crusted over, also lava flows from a little bit further back in time. Right? So from the first few days of the eruption, you just see in the top left here. So that's the pattern of the 6-day eruption, with one last thing I'll throw in here, which is that the crater floor was shown to uplift in the southwest portion, but in the recent days, it actually can be seen to be sinking in that eastern section as well. So the crater floor is still adjusting following the eruption, and we'll have to wait to see what comes next. And that's the Hawaiian Volcano summary for this week. So we'll come back to this time lapse here in a bit, but I thought we should start off, as we have in recent weeks, with our hazard summary, which comes from the VOG Measurement and Projection Project at University of Hawaii at Manoa, the VMAP project, as you see here. And their forecast dashboard for today looks like this. This is showing the next couple of days of forecast of VOG across Hawaiʻi Island. And because the gas emissions have dropped dramatically, we're now down to 250 tons of SO2 per day, which is affecting mostly the nearby downwind areas, the typical candidates here: the volcano, Pahala, Naʻalehu, Ocean View, for the most part, this area of Hawaiʻi Island. This is much different than what we saw last week, with the massive amounts of VOG wrapping to the Kona side, all the way to the Waikoloa area as well. We can see, if we turn to windy.com, here is that global map. If I zoom it in, Hawaiʻi Island is right in here. And this is the layer that's showing the SO2 as a satellite sees it, showing that where we are here on Hawaiʻi Island, we're in this yellowish zone here. So still some foggy conditions, but much of this SO2 plume has been traveling towards the mainland and seems to be currently, let's see, I'll rewind this back in time here. Let's see, put it back to Thursday right now. Seems to be currently between the mainland and Hawaiʻi Island. If I play their forecast animation of how this fog cloud moves, you can see it actually works its way across into British Columbia in Canada. It sweeps down across the west coast into California, and also makes its way into the interior of the continent as well. So that's Thursday. Let me just jump it forward here to Friday and Saturday. And by the end of Sunday here, your forecast you see bringing that fog across Northern California, Oregon, Washington, Idaho, and further on. So interesting to see that getting carried away. Whereas locally, we'll turn to our Purple Air Citizen Science Monitoring Network. These are instruments that people can buy and install in their own homes and join a network, and they get populated on this website. So you can see, compared to last week, a lot of green on the map, no more reds or oranges, especially here on this Kona side. So even though that giant cloud of SO2 gas is flying across the Pacific Ocean, locally in Hawaiʻi Island, things have drastically improved as far as air quality. So that's the hazard summary. And with that, we'll turn to some monitoring. So let's get that on the screen here for you guys. And starting off with a review of the updates the USGS has put out. I'm not going to read everything on these pages, and I'll try to go slowly and highlight the important parts. But last week on Friday, the day after our last update, the volcano was still in eruption, still going pretty well. So most of that update relates to the eruption conditions on that day. For example, they mention spattering of lava with fountains of 10 to 15 meters high. Yeah, that's about 30 to 45 feet high there. They mention lava flows traveling in north and west directions from the vents on that downdrop block area. They mentioned that southwest part of Halemaʻumaʻu, not near the activity, was still uplifting, and in total recorded 10 meters or 33 feet of uplift in that location. They also continued to update SO2 emission values, right, with 20,000 tons per day being the working value just a week ago. So that was Friday's update. And come Saturday, they note that there are some slowdown of activity at the eruption site. So they note here, the eruption continued at a greatly diminished rate, and highlighting a few important phrases here. They say that at several events on the morning of Friday, that activity greatly decreased, but not all events. There was very little fountaining since 7 a.m. on Saturday, with lava still flowing mostly to the west onto the crater floor. And that was the update on Saturday. By about noon on Saturday, the lava flows had actually stopped. So by Sunday's update, the USGS issues two different notifications. One is what we call a VAN, Volcanic Activity Notice. These are the special updates reserved for major changes in activity. At that point in time on Sunday, the USGS dropped its volcano alert level from watch to advisory, and from aviation color code orange to yellow as well. They have a few notes in this announcement that the eruption end was called based on visual and geophysical observations, that SO2 emissions had decreased to near pre-eruption background levels, and all the other updates with the lava we had just mentioned as well. So that was the VAN, but also on Sunday, they issue another update that's a little bit more detailed, and once again highlighting some important phrases here. They, for the first time, note the eruption of the Kilauea summit eruption that began September 10th, stopped September 16th, and is unlikely to restart. That's an interesting addition there. No unusual activity along either rift zone. So more details, they note that the activity, eruption of lava from fissure vents, stopped around noon on September 16th, with no activity visible the following day. They say that the spattering ceased approximately 11:15 a.m., so lava flows seem to persist another 45 minutes to, we'll call it an hour after that. Overnight, the webcam views showed incandescence in the eruption area as the lava cooled and glowed through that hardened crust. So that is most of the update from Sunday that's worth highlighting for you guys. They do note SO2 emissions decreased as well, but at that point in time, 800 tons per day on the last day of eruption on the 16th. Right? So starting off at 190,000 tons, drop down to those 40,000, 20,000, 1,000. Now we're down around 240 was the most recent value reported for us. We'll get to that here shortly. So coming Monday, they restate the eruption is unlikely to restart, but they do add some context here. We do not expect the eruption to resume based on the behavior of past, short-lived summit fissure eruptions. And these occurred in 1982, in 1975, 74, and 71, all of which ended abruptly. So all those eruptions, very quick ends, and based on that, this one ended quickly as well. That is likely the end of that. And here is our 200 ton per day SO2 measurement for September 17th. So that's most of the context. There is one final thing to note, which is that with that downgrade of alert level, the USGS has reverted back to weekly updates on Tuesdays now. So our most recent update is on Tuesday, and it's the only one we'll get until next Tuesday, unless something changes. And in this update, the volcano is not erupting with no significant changes. Otherwise, all the other text is repeated from what we've highlighted for you guys. And that's the text the USGS has released for us this week. All right, hopefully that was a good pace for our ASL interpreters, who advised me that I need to collaborate a little more conscientiously here. So here I am. All right, so to our monitoring signals and then our interview. Over the last week, here's a summit tilt, generally upwards, with variations appearing like deflation-inflation cycles superimposed upon a recovery pattern. This would be easier to see on a month plot, but for now, we'll look at the week to compare it against the summit lava depth plot for the last week, which is what you see here next. So these are meters on the left in the last week of time along the bottom. The eruption actually ended around noon on the 16th, so somewhere right around in here. So to see the crater floor rising during that eruptive time, no surprise there. It was rising upwards, seemed to stabilize for a good number of days here. But here's a curiosity. On the 19th, right, that's just 2 days ago, so Tuesday, there was another increase in the depth of lava right there. It looks like it goes from about 410.8 to 411.3. So that's 0.5, about half a meter of uplift in that same area, which is likely due to settling of the crust. We had a similar thing happen in an eruption back in June, where we saw a few days after eruption was actually over, a change of the depth of the crater floor and ooze up flows on the other side of the crater at the same time, seemingly because lava was pouring only onto one side of that crater and making it unlevel. And after everything had settled and stopped piling on, then it has a chance to re-equilibrate a little bit. So that's what we believe happened in June. And for now, that's my personal working theory and what this signal actually means here. And when we look at some time lapses towards the end of our broadcast today, I do believe I see a couple of spots of ooze-up flows visible in the wide-angle views at this exact same time, close to this time here, around the 19th as well, right? So if you stick with us long enough, we'll get around to that at the end here. So interesting adjustments still happening here at the end. And interesting to note that as this area in the southwest rises, the video we showed you in the intro of the eastern part of the crater floor also seems to be sinking in. So it really is like a seesaw moving with this adjustment here at the end. Looking at our earthquakes, here are our earthquakes over the last month along the bottom here, and depth along this axis. So these are colored by depth. This is just to show that the earthquakes that led up to our eruption, the shallow ones, seem to have quieted quite a bit, while the deep earthquakes still continue at a fairly similar rate here within a normal variation. It's a little more context because when we squish all these deep and shallow earthquakes together, that's what gives us this plot here. So we can see that the total rates have dropped significantly, corresponding with the onset of eruption. And since then, there are still some earthquakes happening in the background. But as you have just seen, those are split between the deep part of the volcano and the shallow part of the volcano, both happening at very low levels. We did have a question in one of our recent streams about this red line on here. So the way that this plot works, just to go through it a little bit more, the blue bars are earthquakes per day. Right? So upper value 250 here, lower value here is probably 20-ish. But the red line corresponds to this scale on the right side, cumulative moment. And moment is a measure of energy as released by earthquakes usually, right? So the difference being when you see a big jump like this, that's normally either one really big earthquake or several moderate-sized earthquakes, rather than lots of little ones. Lots of little ones will give you this kind of pattern. And whenever you have one of these jumps, that's telling you have a bigger release of energy through bigger earthquakes. So you can see the earthquakes release that big energy, open the vent to the surface, eruption begins, and then everything quiets back down to background levels. As far as our lava depth, there it is again for the whole month, that whole raising of that southwest part of the crust. You see a little bit of that detail in here, but I paused earlier in a week-long plot because you really don't see it that well at the scale. It does show here the amount of height gained of that surface in the southwest since the eruption began. And over that same month, here is our summit tilt, showing the full scale of the pre-eruption inflation and then the relief as eruption begins. The turnaround point came right after our update last week when we were wondering about whether that would signify the end of the eruption, noting that in a June eruption, that was how it went down. And similarly, not long after we saw the switch from deflation to inflation last week, the volcano did start winding down as well. Here you see that deflation inflation superimposed upon that pattern a little more easily. So there is that kind of an exhale as lava comes out of the ground. And here is the recovery phase, which would generally head back up this direction with the deflation inflation cycle superimposed upon it there. So looking to the south, the Sand Hill Station shows us same patterns in both components. I won't rehash that. So it seems like all areas of the volcano are deflating as a result of that eruption and now recovering as well. But areas only around the summit, because here at the East Rift, we can see the tilt meter is still showing deflation on both components, no changes there. As far as the SO2 coming out, we have our funny scale here because we now have times 10 to the 5th tons per day. So this is really how many hundreds of thousands of tons per day do you have? So almost 200,000 was the peak for this eruption. And as I mentioned, we're now down around 200 tons per day. So really 100,000 tons per day, right next to that zero marker on there. This is the integrated measurement for SO2 across the whole volcano, which requires the scientists to be able to take a measurement looking at the sun with clear skies, the right time of day. We'll hear a little bit more about that later. But we also have spot measurements at certain locations in the downwind parts of the volcano, including this one at Sand Hill, which you can see is spiking up close to 12 ppm of SO2 on a raw, and come back down to background values since the eruption is over. We see here at Cone Peak, it was 1.5 ppm, and that PKE station was 7 ppm. So you can see certainly some big effects there, and spot locations. Right? It all depends whether the plume itself drifts over this particular instrument and to what degree, to what level you actually see it pick up on the graph. So those are our SO2 measurements. And here's our plot for the whole last year, showing our most recent coming down trend like that, following the one that happened in June, which follows the one that happened in January. Right there, we're probably missing some of the upper parts of these graphs here, just due to the timing of the eruption, not catching the higher parts of this curve as we see today. So for the last year, here's the earthquakes, dropping down to very low earthquake counts per week, as expected. And in that same year, here's our GPS showing, let's zoom it in, showing that offset from eruption. It kind of mirrors the tilt line, to be honest, right? It comes up quite a bit, and then comes down, recovers, and then it goes through a little bit of a wiggle right through here, perhaps corresponding to deflation, inflation as well. So everything is as expected on the volcano with the monitoring signals, including that down on the east rift zone at Pu'o'o, the volcano is still contracting and pinching closed with no change in activity. So no reason to be worried down on the lower east rift. The lava is not coming out of the ground right now, but it's only building at the summit. There is no indication of it moving underground towards habitated areas at this point in time. So just finish off the monitoring here. Earthquakes for the last week look like this on the USGS plot. Only a few spread across the map. This is where earthquake counts come from. It's counting everything on this map. For comparison, here is a full last month, which includes the whole build-up to the eruption, showing how many more earthquakes we were having compared to now. So that's the main signals that we have. I thought I would include a couple of images in this part of our update, since they do relate to the monitoring of the volcano as well. We do have some thermal images, like this one released by the USGS on the 14th, a couple days before the eruption ends, showing the fountains at the vents, lava feeding into the crater, the outline of the old crater in the areas that were hot as well. So when we say lava was pouring into the crater, we mean it's coming from these vents, a down-drop block here, flowing into the pit this way. And when we say it's flowing across the down-drop block, we meant it was flowing around this edge as well, which early on was rejoining the main flow, but as time went on, this branch of the eruption ended first. A couple other comparisons here from the 11th to the 14th. And so we saw this one on the 14th just now. And you see how earlier point in time, that flow is much stronger down the down-drop block and covering much more of the main crater floor as well, all the way over here. Not only that, you see there were more fountains active. You see more of these bright yellow spots here, which are the places lava is shooting up from the ground compared to a few days later here. So that's been a progression of the eruption here. Happened quick within the 6 days. As we mentioned at the top of the program here, the USGS did take thermal scans of the crater floor in successive days here. And so you see the change from the 11th to the 12th to the 14th to the 15th as that eruption focused around these main vents and down-drop block. Any output went down dramatically after the first couple of days. So we do have a reference map released by the USGS on the 14th as well, showing an updated footprint of active lava in red here, but also in this more pink color, where lava from this particular eruption of September covered a crater floor as well. The purple is what was covered in June. Right? And interesting to note that if we follow the trace of the old crater, it was actually like this. Eruption in June was similar to this one in that it erupted on that down-drop block as well. The southwest down-drop block covered it almost entirely here, right? And poured lava into one part of the crater floor. In that case, it was the southwest. Whereas our more recent eruption also began on a crater floor, worked its way onto a down-drop block, in this case to the east, focused its eruptive vents also uphill at a higher elevation than its crater floor. Both of them poured lava downhill into the pit. But in this case, it piled up on the eastern side and tipped the crater the opposite way from June. We don't have any volumes reported yet. We'll have to wait for the USGS to announce those. But we do have the active lava extent decreasing to 100 acres by Friday, with a full extent of coverage, more relevant now, of just under 500 acres or over 200 hectares. I thought I'd pull up this map from the June eruption. This is eruption that went from June 7th to the 19th. And I just wanted to share with you guys that this final map with the actual volumes here was not actually published until July 21st, so close to a full month later. So we'll await and we'll follow up with these maps when the USGS releases the volumes of lava and eruption rates and all of that in more detail. So for now, all we have is that 500 acre figure and our time lapses to go by. So those are the thermal images here. And there's one last thing to cover would be our recent earthquakes on Hawaiʻi Island. This is earthquakes for the whole past week. We have our background ones around the island, around Mauna Loa as well. Pahala cluster is the main action on the island. Whereas on Kilauea, for the last 7 days, here's how few earthquakes are showing up. So really quiet seismically in a volcano. All right, so that's the first half. At this point in time, we'll transition to our interview with Dr. Ken Hahn from the USGS HVO. Dane, do you want to lead into this a little bit? Those are the
sure.
And there's one last thing.
So we were able to sit down with Ken Hahn today, the scientist in charge, USGS HVO, and do a little
feedback again. We have our background ones around the island, around Mauna Loa as well.
I don't know what you're.
I hear myself talking. Sorry. It's better.
That's why I was trying to delay until I talked, so because it should be okay. But all right, so I changed it back over. But yeah, we have Ken Hahn from USGS to go over some of the recent eruption and answer some questions that we had and that we were able to take from the previous chats as well. So about a half hour this interview. So yeah, we're gonna hop on into that.
All right, and let's try to get it set up here. Give us a few seconds to switch our normal setup around, and let's see what we can do here.
Changed it back over, but yeah, we have Ken Hahn from USGS to go over some of the recent eruption and answer some questions that we had and that we were able to take. All right, we are here with Dr. Ken Hahn, the scientist in charge of USGS HVO. He's been so gracious to join us today. We're going to talk a little bit about the recent eruption. How are you doing today, Ken?
I'm doing great, Dane. Good to be here with you and Phil. Thanks for inviting me.
It's good to see you, Ken.
For sure. So we got a series of questions here, and some of them from our community and some of them from ourselves that we'd like to go through with you and just recap this recent eruption. Pretty short little one. You want to take the first one, Phil?
Yeah, well, just from your perspective, what made this most recent eruption unique? We know we've had a lot of eruptions this year and recently. In your mind, what makes this one unique?
He's been so gracious to join us today.
Well, I mean, first off, it was the first one that really had a well-defined fissure and fissure cones developing and stuff. So it was a beautiful eruption, and it was really visible around the summit. So there were a lot of good viewing areas to see it. So it's fantastic that way.
Stop that and fix the audio issue. Just recap this recent eruption. Pretty short little one. Sorry about that.
You want to take the first one?
Overlapping audio. Yeah, I'm not sure what that's.
Yeah, well, just from your perspective, what made this most recent eruption unique? We know we've had a lot of eruptions this year.
Oh, it must
and
be.
recently.
Okay, let's try.
Seeing
if the audio is
really
working.
gradually from the 2020 and the 2021 were more typical real Halemaʻumaʻu sustained eruptions. And what we've seen since January of this year is a shortening of the eruptive period and switching over to more like.
Gonna go ahead and restart. All right, we are here with Dr. Ken Hahn, the scientist in charge of USGS HVO. He's been so gracious to join us today. We're going to talk a little bit about the recent eruption. How are you doing today, Ken?
I'm doing great, Dane. Good to be here with you and Phil. Thanks for inviting me.
Good to see you, Ken.
For sure. So we got a series of questions here, and some of them from our community and some of them from ourselves that we'd like to go through with you and just, recap this recent eruption. Pretty short little one. You want to take the first one, Phil?
Yeah, well, just from your perspective, what made this most recent eruption unique? We know we've had a lot of eruptions this year and recently. In your mind, what makes this one unique?
Well, I mean, first off, it was the first one that really had a well-defined fissure and fissure cones developing and stuff. So it was a beautiful eruption, and it was really visible around the summit. So there were a lot of good viewing areas to see it. So it's fantastic that way. What we're seeing really gradually from the 2020 and the 2021 were more typical real Halemaʻumaʻu sustained eruptions. And what we've seen since January of this year is a shortening of the eruptive period and switching over to more like short-lived fissure eruptions. And then this one was just really like a typical fissure eruption. Comes up, we get a crack, and the fissure came up outside of the Halemaʻumaʻu area that has all the lava ponded. It has 800, 900 feet of lava ponded in it. So that changes the fissure dynamics. So we get kind of a straight line of vents, and we got the kind of what typically are called curtains of fire, which is not scientifically endorsed, but it's a very poetic way of looking at the eruption, right? And then it settled down to those cones and spattered, and those cones. Sorry, there's a C-130 just flying over right now. But those cones, they look kind of small when you look at them on the cameras and stuff, but each one of those cones, the big ones, were 50, 60 feet high. So they were substantial structures. And so anyway, it was a really nice summit fissure eruption. It lined up on one of the historic fissure. We have these alignments. This is the one that goes kind of from the northeast corner of Halemaʻumaʻu over towards Kilauea Iki. Same kind of fissure setup that the 1959 eruption of Kilauea Iki took place on.
Interesting. So to follow up on that, you mentioned that the pattern is shorter compared to previous years, but do we have any idea why that might be?
Well, I mean, what we're seeing right now since 2018 is reestablishing the plumbing pathways up in the summit, right? Particularly the shallow pathways. And so there's been a lot of compressible space because, as we know, during that collapse, there's a lot of rubble underneath there and things. So as the magma works its way back up, it's displacing that rubble and also compressing the rubble. But none of that is very predictable, right? How it's going to, what it's going to be able to get out of the area to rebuild a shallow magma chamber, because it's clearly working on that. And it's also working on whatever these pathways are to the surface. Right. And so we see it pressurize as it's going through. And what we saw that the last couple of months between the June eruption and this eruption, we saw that pressurization taking place and reflected south of the caldera. Right. But ultimately, the failure appeared inside the caldera. Right. So that's where it was able to release the pressure by coming to the surface there. And there was a lot of stored magma in there. Right. So clearly we're still getting magma from the mantle coming in probably at close to the same rate, and we had very high effusion rates. This eruption was more approachable since it was on what we called the downdrop block, which was a piece of the caldera floor that was downdropped into Halemaʻumaʻu. Eventually, it's going to be annexed by Halemaʻumaʻu. It's working on it. very.
It's a good way to describe it right there. Annex.
Yeah, it is. As you fill up the old Halima'uma'u crater, right, and it's lapping onto that down-drop block, pretty soon there'll be no boundary between the down-drop block and Halima'uma'u crater proper. So it'll all become a new enlarged Halima'uma'u crater at some point.
All right.
Yeah, it's really interesting to think about how that name changes. The actual landscape changes over the year and the name stays the same, right? It's really fascinating. Go ahead.
Yeah,
Dave.
well, it's typically, I think, the site of the eruptions and, the Homa Pele, if you want, it
Right.
is, there's a reason why that area is sacred, and it is really where the life of the volcano lives, right? And as we all know, the volcanoes are very different when they're erupting. You really feel the earth is alive when an eruption is going on, and then when it all goes silent and dark again, something's missing, up there. So.
Right. It really is just, awe-inspiring to me to see how fast everything's been moving since 2000, and including 2018, from the collapse to the water lake to now, a half dozen plus eruptions and 3 this year. It just ever changing and always something new.
Well, I don't think anybody would have predicted in 2018, after we formed that 1,500-foot hole, that by 2023 we'd filled in 1,000 feet of it. That would have been
That's pretty crazy.
So the volcano has been busy, right?
Yeah. I wanted to ask you a little bit about the gas, the SO2 up there. So one thing we saw with this eruption was that SO2 reading on day 1 was incredibly high compared to the SO2 readings we've gotten off the previous ones. We were wondering if that had to do with maybe the timing at the that you were able to get a reading in the early hour or 2 of the eruption, or something along those lines, versus the previous eruptions. There might have been a different time delay. Was this eruption, did it have more gas, or was it more similar to the previous ones?
We think it's probably similar to the previous ones. And, a lot of the other ones erupted at night, and our gas measurements rely on having the sun, right? So what we're looking at is the color of the sky where it's clear versus the color of the sky where there's SO2, and we're measuring the UV light penetration of those things, and that gives us an idea of what the SO2 concentration is. So we need to have the sun up, right? And preferably midday kind of situation. So early morning, late afternoon are hard. So we need an eruption that takes place. This one complied and erupted at 3:15 in the afternoon, which was just in time before the sun got too low angle for them to get out and get a measurement. So this eruption was great for us as scientists because it was more approachable. You didn't want to be down in the bottom of Halima'uma'u crater in 2020 when lava was erupting in there, right? And you couldn't actually access it. But since it happened on this stable piece of the old caldera floor that had been down dropped, we could get people down there. What we tried to do was really sample this one as much as we could, measure the gas as frequently as we could. And then we also did overflights so we could measure the changes in volume in the crater as well, to see if our effusion rates match the gas. And it's not perfect, right? I mean, everything, like we say, oh, that was 193,000 tons a day. Well, that's a spot measurement. That measurement didn't last for a whole day. That amount of gas, it quickly tapered off. So we should probably be looking at it in tons per second or something like that instead of tons per day in these measurements, the same way we do effusion rates in cubic meters per second. But even that, right, we didn't get a flight till Monday afternoon to look at the change in the surface area and the depth of the craters, which is, we're just making volume measurements, and then we're dividing it by time. So it's always an average that we're looking at over a time period. And so, it is one of those things that measuring it accurately is really difficult. We know that both the effusion rate and the gas rate work together, and they both drop exponentially in the first few days of an eruption. It's just really hard to put real hard numbers on those things.
Yeah. One, just follow up on that if I can real quick. The SO2 emissions. So we saw how Kinakikoi and Waldron's Ledge were closed in the first day of the eruption. And it mainly because that plume had been, with the downdrop block eruption, the plume had been moved over closer. So now it was coming towards the Kilauea overlook. But I was just wondering about, how does that process of like closures between maybe USGS advising on a national park, then making a closure or anything along those, how did that transpire essentially?
Well, I mean, a lot of that is the park deciding. They had people out there first at Kilauea, and they were looking, and there were two things going on. One is, the very high volume. Well, three things really. The high volume, the fact that we had fissure vents open up over in the wall of that crater over there, not very far from Kilauea, right? Very close to it, there were vents open. And then the third thing is the wind was at an odd direction. It wasn't normal trade winds, so that the wind was blowing things more north-south than northeast-southwest, right? So the plume was naturally closer and swirling over by Kilauea. And so we put our gas team out there for quite a few hours on Sunday after they made the gas measurements. They were there through the night, and they were actually measuring ppm sulfur and stuff. And it was getting pretty close. And the park, what they're concerned is that while they want to get people to the maximum viewing area, they also want to assure people's safety. And if you've got hundreds of people down there and all of a sudden the plume comes over you and the kind of concentrations that were coming out at that point, it would be very difficult to get people out. And as you guys know, it's not just the concentrations, it's also that your eyes well up and tear and you can't see, and so you got a bunch of people wandering around in the dark out there in the plume. So the park makes those decisions based on safety considerations for visitors in addition to viewing. And quite frankly, the viewing wasn't as good over there as it was from like Kilauea Overlook and stuff, where you could look perpendicular to the fissure instead of down it, because what happens when you were looking down from Kilauea, the gas coming out of those closer fissures was really blocking your view of the fissures, the fountains further down. So,
awesome, thank you.
You've mentioned the high effusion rates along with the volumes. Do you have any preliminary estimates that you could share with us?
I don't right now. I'm sorry.
Fair enough.
That's fine. They're still working through all those numbers, I think.
Is it generally similar to past eruptions?
I would think that we're looking at starting off in the over 100 cubic meters a second and then dropping down, and this one just dropped right down through, and it didn't even level off. The long-term rate, the sustainable rate where magma coming in equals lava going out, is about 3 to 5 cubic meters, or if you want, just 3 to 5 cubic yards. Slight difference between them, but you can think of it as cubic yards as well. So like for the 2020 and the 2021 eruption, what you had was the volumes and the gas dropping right down to that long-term sustain and then leveling off like a plane in flight and flying along that pattern for months, right? And so this one, though, just hit that barrier and just went boom right through it. And so there was, it didn't go through the long-term sustained rate. There wasn't enough pressure to keep this thing going, and so it just shut off. And that's pretty typical of the behavior of true fissure eruptions that we've seen in the summit before.
One thing that makes it a little bit different that we heard about was the uplift of the southwest part of the crater floor, right? And the lava was injected at least underneath that part of the crater floor based on a laser rangefinder that's pointing at a place that was not covered in lava. Is that correct?
Yeah, well, that area, the old area that was the center of uplift, is still the center of uplift. And so if you notice that a lot of the lava that came out of those fissure vents, at first it covered the surface, but a lot of it actually, because some of those fissure vents actually pierced the crust of the lava, stuff was draining underneath the old crust. And we know that the crust along the margins of the crater out there, particularly if the actual crater dimensions up at the top now, it's like a funnel, right? So those wide ones, the real crater crust is defined by a much narrower thing. Back when it was much deeper, it formed a crust. And then as it continued to uplift, newer crust formed in a ring around it. that crust thickened by lots of overflow. So it's extremely thick out around the edges and thinner in the center, particularly over in that western or southwestern area where the old lava pond used to be. And so it's actually still, there's a couple points of glow where it's still degassing at night. That's the last points of glow in there too. So we just think the crust is thin there. So that dome stayed, and that dome uplifted by 30 feet during the eruption. So pretty spectacular.
It really was. Yeah, to see that with the pointing with no lava and seeing it coming up, that was really cool to see. Along those lines, there were some distal flows that over there in that, I think it was the northwest part of the caldera floor, that have been debated whether they're actually ooze-up flows or crustal overturning of that initial first outburst of lava. Have you guys looked at that at all and have any insight?
I saw those, and it looked like the weight of the other flows, the surface flows coming around, kind of broke the crust, and there was some of the older stuff that oozed up, but we haven't been able to get over into that area. It's too hot and shelly, and that all got run over eventually by the shelly stuff out there. So yeah, no, it's we've had people down, the last flight down was on Monday, and tried to walk across some of the new lava, and it was pretty impossible. They went
So it's
out
all that, it's all that shell pahoehoe that
yeah, it's all very hot shelly pahoehoe with very thin bubbly crust that's easy to break through. And you know what it's like dropping into a hole full of razor blades,
That's very hot.
Yeah, hot razor blades. Yeah. So it's very hard to work out in there.
Yeah, so you've mentioned that the location on a down drop block has made sampling a little bit more accessible because of that location compared to the previous eruptions. And you guys have pictures of scientists collecting pieces of tephra from lots of those little cones.
I think there's quite a few of those already posted on our website, and there'll be more coming up as well. I know on Monday they found the old Halima'uma'u crater floor trail, right? The Halima'uma'u trail. And it just ends in those lava flows. There were a couple of the ahus left down there, and so yeah, they were down there and picking things up and looking very scientific. They were picking up rock samples and putting them in target bags. So
you have any preliminary results of compositions or possible magma sources?
The compositions right now are looking very similar to the prior summit eruptions. So we think, there hasn't been a lot of change in the bulk chemistry of the magma system. And that fits with what we've seen, because we haven't seen, one of the things that in prior summit eruptions, a lot of times you would have drain back events after these. We've had zero drain back after any of these eruptions, which means that we have positive pressure in the system. And that positive pressure is kept because there's no escape to the southwest rift zone or to the east rift zone, right? So we're not seeing magma move out of the summit out to one of those rift zones where it could cause a draining of some of that shallow material back into the summit. When it goes back into the deeper magma chamber, it stirs things up and mixes them, and oftentimes you get a change in composition because of that drain back and mixing. But we're not seeing any of that drain back. So the chemistry is fitting with that model, that we're just seeing kind of the top of the deep magma chamber being pushed up into the shallow areas and erupted. And so that top of the deep magma chamber is much higher volume than what we see in any individual eruption. But it's sitting down there and it's staying a fairly even composition at this point.
Awesome. So one of the things that we were watching, obviously we're watching the live cam. That thing is really cool. I'd like to commend you on the USGS HVO's progression into being able to share more footage, more video, more audio, all that kind of stuff. It really is.
Just comes down to money.
You got to put the quarters to feed the system, right?
Yeah, it's quarters, but you can imagine, those are on cell phone modems. And, like our Mauna Loa cam, the reason we're able to do that is because our chief field engineer, Kevin Kamibayashi, he has converted us over to the first responders net, which has lower prices and stuff for things. And you can actually imagine that you want the 500 gigabytes a month plan or 1 terabyte a month plan on your cell phone. Imagine how much that costs if you can't get it on a commercial one, right? Say, I want a terabyte a month. And that's basically our streaming for one camera is somewhere between 500 gigabytes and a terabyte per month. So we use that, and it costs thousands of dollars on Mauna Loa, but we can do it. We also have one grandfathered in cell phone modem that has unlimited data plan that they dug up back in the East Coast for us and sent us. Hey, I think we bought this thing, a long time ago, and it says unlimited. And so far, the chickens have not come home to roost on that. So that's the one that's out there right now. We circumvent a lot of that because we don't actually stream it live into ours. We're streaming it straight to YouTube. We're not storing it on our system or anything. And, we really keep our own personal use of it down to when we want to reprogram the camera to move it in different places and stuff.
Right. No, it's really good. Yeah, there's a whole bunch of little things about it. Like I just found out myself just going outside a little bit, but after 12 hours, right at the 12-hour mark on a live stream, so you've been streaming for 12 hours of the eruption, if you go past that mark and the stream ends, the video gets deleted. Essentially, YouTube deletes the video. So like one of the things we saw recently was when the live cam got back up, it started turning off at like 11 hours and 39 minutes and stuff like that. So it was like maybe they figured, but there's little things that you got to work around, essentially, like work within the confines of another platform.
Yeah, all of that is handled. We're not allowed to stream directly to YouTube, so it's handled by our folks back at headquarters in Reston, Virginia. So it's done through our IT and communications group back there. So when we lose the connection to there, and I don't think it's really as organized as what you just laid out. Would be nice to be that organized. But I think sometimes the camera loses its connection. And so we did have a connection right at the end of the eruption. We had a connection loss, but that was a real connection loss for the video. We were still getting stills in from the camera, so we knew it wasn't the battery and stuff. We had another one a while back, and the battery died, and so we had to go out and replace the batteries on the station. But this one was because it lost the connection somehow and had to be rebooted. So. And then rebooting it, then every time we reboot it, we have to start a new instance of the YouTube channel.
Yep.
And that's why all of a sudden it says you can't, this is no longer streaming, because it won't let us pick up that old instance of the stream and continue it. So yeah, it's a little inconvenient for viewers, but I think most people hunt and peck around and find it again.
Right. Is there anything new in terms of the tech that you have planned, like new tilt meters or SO2 monitoring, anything along those lines?
We're working on things, but they're all in process. We have a couple of SO2 cameras out there that can actually see the SO2. They're basically cameras that instead of using the regular spectrum, they only see in UV light. And so you can see the plume on those. But there's we're working with a group from University in England, and there's a lot more developmental work before that ever comes online. We're also trying to key in the old, what we call the fly spec, where there's a series of computers and SO2 detectors just out in the Southwest Rift Zone, and they all died during the 2018 eruption. And we've got that back online, but we're now using a different spectral technique than those use. And you can't actually recalibrate those. The guy who actually made the gas tubes that calibrated those is no longer working. And so it lets us know, and sometimes it's pretty accurate, but it depends. It was made for a certain wind direction and a certain vent location, So we're working, we've done a lot of work to bring that back online so that there would be almost continuous daylight measurements, but we don't publish that out there because it's not completely accurate, particularly at the low SO2 reading. So we're still working on that, and we're going to convert all the spectrometers out there into the newer spectrometers, but that's more of a long-term it'll be another year or two before we get that thing up and completely running and calibrated again.
Very good.
So yeah, we're doing those kind of things. We're still working on trying to calibrate taking a regular video camera and turning it into a pyrometer so that we can look at maximum temperatures. The thermal cameras we have out there right now have pretty big pixel areas, and so they kind of average the temperature. So we're never seeing the magmatic temperature on those thermal cameras. You're just seeing it's really hot, but it's not the maximum heat. So we have a Sony camera that can take raw images, and we have color calibrated those using a special furnace that's called a black body furnace, where you heat up a uniform piece of metal to different temperatures and it glows different colors. And so we have a specific setup in this camera to look at the color, and we're still trying to work this. It's how the guy who's working on it has worked on some of the Galileo satellites and other things that we're doing the temperatures on Io. So we're kind of taking that space kind of technology and applying it to an off-the-shelf camera and trying to kludge it into doing the same thing that a $500 million satellite does.
Just MacGyver it together,
Yeah, well, it's a lot of what it is a lot of brain thinking, and how can I apply this certain set of formulas and stuff to take this color and turn it back into a temperature, right? So there's a lot of complex math that's going on in there, and you run into complications thinking, oh, this should have worked, and it doesn't. So now they got to figure out a different way to go about, different set of equations to use to do those conversions. So there's a lot of high level math in that conversion stuff to get that to work. But it's still promising that it'd be nice to have this camera with really high powered zooms, and you can take like 12 frames a second of these raw images, and then just have a program that goes through and searches for the maximum temperature in those and see if that equals what we measure the temperature by chemistry. So it'd give us a way to immediately, not quite on the spot, because you still have to take it back to the lab and analyze the images, but a little bit faster than analyzing the rocks to get the temperatures.
That's a new frontier. There's a long tradition of development of HVO, water tube tilt-meters, back when Jagger would stick the different compositions into the lava lake for temperatures. So it's awesome to see.
Those guys made they made the first high temperature thermocouples, by using the difference in resistance between two different kinds of wires tied together, So, they started the whole, really, that high temperature thermocouple business used in measuring volcanic temperatures. So, and, we would use those, but you can't really get to this, right? Same problem with Mauna Loa. You can't really get there and take temperatures very easily because the things are so big and so hot. And then you don't, when you move to the edge of things, you're not really measuring the maximum temperature. You're measuring something less than the maximum. So that's not necessarily, it's close, but it's not like horseshoes. It really doesn't count unless you get the maximum temperature. It can be misleading if you get something that's 10 or 20 degrees less. That's actually a lot less in the kind of stuff. It has a lot of different implications for how the magma is going to behave downslope, right? Yeah, for instance, in the Mauna Loa eruption, we did the rapid turnaround chemistry, and we saw that the magnesium content of that lava was, instead of being up around 6.2 or 6.6 or 6.7% magnesium, it was down around 6.2, which is the lowest that's ever been measured on a summit eruption of Kilauea or Mauna Loa. And that told us right from the get-go that this stuff was way down below the crystallization point, and that it was going to really have an issue when it got to the flat ground down there. Our main concern with that eruption in Mauna Loa was not knowing Mauna Loa on the northeast rift zone.
Another C-130.
Yeah, I don't know if you can hear those or not, but my office is right in the takeoff and landing pattern for the Hilo airport. So I can monitor all the interesting different aircraft that come in and out besides just the inter island flights. when you look at that stuff, that stuff was much cooler. And so we were worried, though, about that particular eruption, is that eruptions of Mauna Loa on the northeast rift zone, and actually at the one that we had in 1859 that went out to the northwest, they not only had a very high effusion rate initial phase, which all Mauna Loa eruptions share, but they continued for months afterwards. There were certain eruptions that continue for months. And that was the concern, because it was actually following the train of the 1935 eruption, which also stalled kind of on the flats. But then it went into a long-term effusion rate for several months and created a lava flow that goes for a couple miles. And actually the saddle road follows it. When you come up into the saddle at first and you get kind of flattened out, you're following a lava flow. That's the 1935 lava, and that's the longer-term low effusion rate part of that eruption. So the real concern for the saddle road was not from the big lava flow that everyone could see. It was the possibility that a very low effusion kind of creeping lava, more like Pu'o'o, would have followed that eruption. So that, and we don't really have any way to know if it's going to happen or not.
Yeah, so since you mentioned Mauna Loa, was there an effect of Mauna Loa from Kilauea's eruption, or is anything different in Mauna Loa since its eruption last year that you can mention before we wrap it up here?
Mauna Loa is still inflating. It's slowed down. It's mostly deeper inflation instead of shallow inflation. We really don't know. Mauna Loa since 1950 has been in this different pattern where instead of erupting in the kind of 3 to 6 year periodicity it did prior to that, we have these funny things. It's like 25 years, 9 years, 38 years, right? So we've had, Mauna Loa has been erupting much less frequently, but the interplay there is that during the 1800s, Kilauea erupted frequently in the summit, but the total volume of the eruptions were down. And we're in a period now where that's also true, because we have these large gaps in between them. And while the eruptions are spectacular at their starts, they really are not keeping up with what the long-term production rate would be. We don't know how much of that magma that's being generated at depth is just going in to intrude and fill spaces beneath the summit. That's very difficult for us to measure unless there's a really big body that gets filled, right? But it can be, a lot of that can be hiding down there. Or if what we're seeing is that Kilauea magma production is actually down somewhat. If it is, it could be that then when Kilauea magma production was down in the 1800s, Mauna Loa magma production was up. So we're keeping an eye on that to see if there's any way to measure that, because it might portend that there's a behavioral change in Mauna Loa, but we don't see any indication of that right now. But we are watching, and that's a problem we're trying to get our hands on and figure out how to solve, but we can only measure what the volcanoes give us to measure.
All right, maybe one last question. So back on Kilauea, focusing on the rift zones. So we've seen the seismic activity in the upper east rift zone and the east rift zone connector, and more recently at the summit in the southwest rift zone connector. But really, this is a common question. What are we looking for if it's coming back down to where people live in, say, Lower Puna type of thing? What is the sequence that you'd be keen in on before it would move? It would make such a move.
Well, I mean, lower east rift zone eruptions are kind of like Mauna Loa eruptions. I mean, they, you don't really know until it happens, right? Because we have both shallow pathways and a deeper pathway down to there. So we're watching for any signs that magma is moving down in there, and that's one of the things that our GPS instruments are good at, is they can see down several kilometers without too much trouble. Seeing apart, and where particularly we watch, there's a line of GPS instruments out around Escape Road out by Mauna Ulu, and it can see both shallow and deep, and it is still contracting, which the volcano is pulling back together. So if you think of the flank of the volcano kind of like a slinky, that the slinky coils are being pushed back together and contracting, which is decreasing the compressible space out there. And so we're not seeing a lot of magma movement under there, or they would be expanding, right? So the distance would be getting greater. And the way that basically the rift zone works is as you pull on that slinky, because the flank is moving seaward, right? Kind of pulls the slinky and pulls the coils apart from each other. And then the magma can get in between one set of coils and push the other coils together. That's the kind of compression that we're talking about, and make space for the magma to move in one crack, right? So we're not seeing that set up right now. It could change relatively rapidly, but we're pretty happy that, we're not seeing that at the moment. But, even during the summit eruptions, right, when we had these ongoing summit eruptions in the 1800s, we had fissures that went almost all the way to the summit to the sea in 1790 and 1840 up there, right? So,
yeah.
So anything is possible. Nobody should really let their guard down and think that we're completely safe. But I think, we're in a better position than a time when there was a lot of activity down there.
All right. Well, thank you so much for taking the time to join us today, Ken, and be able to talk a little bit about the recent eruption and some of the stuff that USGS HVO is doing.
Sure. Glad to. Anytime, you guys. Thank you so much
right.
for having me on.
All right.
Wow, again. All right. Looks like we're a little shuffled here, but no big deal. Let's maybe try this one here. All right. So mahalo to Dr. Ken Hahn from USGS HVO for joining us for that interview there. I had originally thought we would go through a whole bunch more images and time lapses, but seeing as we're already approaching the 1.5 hour mark, we will defer those until next week.
We'll have a little bit of time to talk about that kind of stuff and go over the eruption. It seems like we're on quarterly eruption schedule right now. Well, this is the third eruption this year. We'll see if we get one by December.
Yeah, so the question came up during a Two Pineapples live stream. There was in 1974 a year where there were 4 different eruptions around the summit. The very last one was on December 31st of that year. And it took all the days of the year. So we'll see if we have something similar happen to us.
Right.
But would not expect it maybe quite so soon.
The third quarter eruption was pretty close. Mid September.
Yeah. So it was an excellent discussion with Ken. I thought he added some great insight, both on Kilauea and Mauna Loa. We tried to pass on as many questions as we could from our viewers, but we were a little bit over time already, since he was giving us such great answers that we couldn't quite fit it all in, but he's willing to come back, and we'll just keep adding questions to our list for the future there.
Right.
Thank you guys for bearing with our audio and technical issues there. We recorded that interview like just a couple hours ago, but we wanted to make sure to have the ASL interpreters be able to join as well. So that's what it took for us to make that happen. And now we have a little practice, so hopefully it will go smoother if we do that again. Yeah, thanks for bearing with us on that. So Dane, all of that said, I think we should open the floor for some questions from our audience here about what we just heard Ken say and whatever else we've covered. And if need be, I'll pull in some more images and time lapses, but we'll not expect that at this point here.
Yep, I had a few questions here queued up, and we'll try and do some of those. These were from more earlier in the stream. But Kenny asks, what do you think of the inflation marking the end of 2 small eruptions in a row? You think this is a permanent trend?
Yeah, that's a great question. That would just be a guess from me. I really don't know. I think, what I would say is that clearly the last 3 eruptions have been much more finicky, maybe is one way to think of it. They are more sensitive to the conditions underground. So it could be that unless something major changes, I would expect more of the same to answer the question there.
Right.
But
yeah,
as we've said for many years, we're always just one earthquake away from changing the system at any point in time. Right. So go ahead.
Yeah, I was just going to say that it seems like trends can emerge, patterns can emerge within moments in time. So for a certain period, The most pronounced pattern that comes to my mind was the collapse explosion duration during 2018, where we were predicting it within the hour essentially and graphing out where it would be, 4 collapses from now, what would be the duration. And then that pattern ended as soon as the eruption ended. It was like, cool, that was a very reliable pattern. We were actually able to make hazard announcements like, hey, there's going to be a pulse coming into the fissure in about an hour and a half type of situation. But that was a temporary pattern, and I expect a lot of these patterns, if they do emerge, they'll be temporary, and then eventually something will change, a big earthquake, and then we'll be looking for the new pattern.
Yeah, the thing with patterns on Kilauea is they're hard to use for predictions because things can change in between. So it's always easier to notice a pattern as it's occurring or after the fact. And it's a lot more tenuous to say, well, that means the next one will be like this as well. Because you just don't know what changes. Every time an eruption ramps up, you have all that pressure building, things are cracking and moving, and eventually it's going to break something. And at that moment, really anything goes, right? And so that's where you don't know if you're going to have a similar to before or something, a whole new kind of eruption. So yeah, really interesting to note the patterns, and I'll be curious on that too, Kenny, to see if we have that same pattern next time. And we'll see. Yeah, if we keep up with these short eruptions that are more frequent, as Ken suggested, since magma's filled in many of that crack in the shallow systems so far. Yeah, it's going to take something big to change that. Considering pressure is building up just in the summit area and not elsewhere. It's all a summit story right now.
Right. All right. We've got a question from JMS, kind of a technical one here, but thoughts on structural control of vent spacing, ring fractures, and radial fractures intersections?
Yeah, we mentioned that on one of our updates earlier during the eruption itself. Let's see what I can show you guys here. So this is that first evolution of that vent, right? And you maybe can see along the bottom here, this is the old edge of the crater right there. So it's hard to see exactly, but we did have early on. Let me see if I can pull it back here. Or maybe I'll do this. Let me find, there are some USGS videos that we'll bring in here later on, but if I can just find one of these early, there it is. That's a good view right there. View of these fissures across the caldera floor. The main fissure line travels in this direction like this, and it connects all of our vents going up. But maybe I can zoom into right there where you see this cross line coming across this way. And this to me seems to line up with the edge of that inner crater. So this is essentially the crater wall. And between the upper part of the crater wall and the lower part, there's a big crack. So that's the crack that I presume lava coming across this way hit that crack and came up that crack as well. So here you almost see this plus sign of fissures crossing each other, right? With as what was the commenters? Is it? JMS, yeah. So as JMS says, yeah, this would be the radial fracture, then this would be the ring fracture coming around right there. So that's certainly, I think he's right on, he or she, JMS. There's also something I pointed out early on that there was actually not just one radial crack, but it seems like there's a step over somewhere in this area over here. And right through there, you may have another one of these ring cracks as well, ring fractures, also maybe allowing this thing to step over a little bit there too, right? And then finally, the last one we mentioned was up against the actual back wall, the eastern wall of the downdrop block. We saw once the lava reached that back wall, intersect that and come up and erupt off of that talus as well. So I do believe that there were 3 different ring fractures intersected here by this one radial fissure that kind of had some really interesting effects. So yeah, great question.
One little comment on that very first one that formed, that first cross. I don't think it was actually the exact perimeter of that, the height displacement there, where it dropped off. It was on the upper block, but it was close, right? So it was like crept up through a crack through that area, but that was interesting because you had the lava falls then coming in until it filled in.
Right. So, I mean, if imagine that there's, as something collapses, it's not always going to be a clean break. It's likely going to be lots of different slivers almost, right? So
right.
it's very likely that that crack connects into that main crack that's going down, and you just had a little sliver
Right.
at the top that was just a little, I don't know, almost like a loose tooth in a sense up there, right? So that is the real crack that goes down. Once you get down to the depth that this fissure is intersecting it, it's the same crack.
Right.
Yeah.
All right, we'll do one more. Sorry, guys, we'll try and get more questions next week. We just had the Ken Hahn interview, so half-hour of Q&A with Ken. Appreciate that one from him. Richard asks, could the next eruption switch back to the west side of the crater?
Yeah, absolutely
play
could.
Volleyball
Yeah.
in there. Type of
Yeah,
thing.
ping pong of some kind. Yeah.
Right.
Yeah, it could be, but once again, the same answer as far as the patterns is what I would say here for this one. It easily could. It could easily go back in the same spot as it is now. It could easily be elsewhere in a caldera. It could be just outside the main caldera on the upper blocks of the caldera walls as well. We almost saw that come onto the main caldera floor with this eruption, right? But in 74, the fissures at Kinekakoi were actually up on the upper wall by where the viewing area currently stays.
Right. I just point out you have two data points there essentially for that one.
Yeah, I mean, it could well be, but it is interesting how it actually what I think fascinating is that the tipping of the crater floor, right? And maybe I'll find that video to play one more time here as we wrap it up here. This is the B2 camera, just a daytime, sped up immensely and looping now, showing well there it is now, it's looping, showing this southwest part of the crater floor rising back here. But also right in here, notice this section is all sinking here towards the end of the video, to the point where you actually see stuff come up through the crust, this little mound forms, right, as the rest of the crust dips down below it there. So I think it's really interesting to note that this time you see the east side of the crater floor was the one that got dumped on, got tipped up, maybe raised the other side, whereas last time it was the opposite effect, right? So very similar patterns from the June eruption to this eruption. In June, it opened in the southwest, covered that southwest down drop block and the southwest part of the crater. In this eruption, it opened in the eastern down drop block and covered the eastern part of the crater. And both of those vents ended up settling at elevations higher than the crater floor and poured into them, one from the southwest in June and then this time from the east in September. So yeah, we'll see if it's east, west, south, maybe. Not too many eruptions in the north side historically, so I'd probably say that's the least likely thing to happen. But we did hear Ken mention the Kilauea trend. You could potentially, it's in play that you could have some fissures opening up towards that part of the caldera as well in the Kilauea area, which Kilauea is actually within the caldera as well. It's just a separate collapse point within that giant crater floor.
All right. Well, I think that gets us through the questions. I appreciate everybody. I want to thank our sign language interpreters, Dano and Carrie, for again joining us. They will be on vacation for the next 2 weeks, but they will be rejoining us. We appreciate them, coming on and helping us out with providing a more collaborative, but what's the word I'm looking for? More accessible, yes, platform and our message and all that kind of stuff. We also, if you want to support us, we do take donations on hvery.org/donations, and that's the main place we do that. Those are tax deductible donations too, so remember, claim that. But yeah, I think that does it for me. Yeah.
I think we're good too. We did have a volcano watch this week that I can mention, but it's about tsunamis, so you can check that out on the websites or on a Facebook platform, and we'll add that in next week as well, since it's not anything super urgent. But the bottom line there is that September is actually National Preparedness Month. So here we are in September. We'll still be in September next month, towards the end of the month, but overall preparedness is good. That is part of our mission. That's why we educate on volcanoes, is so we can all be better prepared for any eruption and habitated areas in the future, right? And to reduce the costs and impacts of any such disaster when it does happen again. So yeah, we'll follow up that next week on that. And we don't have any community events until next month as well, so we will leave it at that. So that's it for me as well, Dane. Any final words?
No, check out hvery.org, Hawaii Tracker on the Facebook. If you're not a part of that, check us out there. And then on YouTube, it's on hvery. And on Twitter, it's hvery_org. Those are our social medias, just to shout them out there.
Right on. Well, thanks for that, Dane. Thanks everyone for joining us. Extra special mahalo to Dr. Ken Hahn from the USGS HVO who joined us today. We're happy to keep passing on you guys' questions and hopefully their answers back to you as well. So hit us up if you'd like to add some questions to the list for next time, whenever that may be. Drop them in our comments. And until next week, Thursday, unless something happens in between, Dana and I will be back, and we will miss our ASL interpreters. They'll be in our hearts and minds until we get them back. It's been really nice to have this addition to our broadcasts over the last month and include them in this past eruption. So big mahalo to those guys, to you guys. So until next week, from HVery, I'm geologist Philip Ong, Mr. Dan DuPont, Daniel and Carrie Kaufman, and mahalo everyone. Aloha.